Well, I'm glad to hear that. I'm glad to hear you're ready for polyatomic ions and molecular geometry. Because some would argue that because I've given you so little bell work to do, that's going to take me 10 minutes to get your attention back. So we can sit here and talk about whatever you're talking about. It's my fault that you're not going to learn for the next 10 minutes because I didn't give you work to do before the bell rang. Is that true? Well, you can say no, but if research says yes, maybe it's beyond your ability to understand the lessening of the learning opportunity you have, for which I will apologize then. So I will try to have a little bit more than just copy down and make sure you have the homework in the future. Let's just start with this. Vesper. What's Vesper? Ma'am?
Valence shell electron pair repulsion.
You can read your own handwriting. That is amazing. Okay, so valence, it's pronounced Vesper, but the acronym is actually VSEPR. But we don't say VSEPR, we say Vesper. But it stands for, it's a valence shell electron pair repulsion. Who wants to explain it for those who are absent? What is valence shell electron pair repulsion? This is where you're looking for your notes to read it, but it's not necessarily there because we didn't give you a short, concise, 3-sentence definition. Vesper is the basis behind which we do molecular geometries, okay? So where do the molecular geometries come from? Anybody want to engage me on that one? Where do we get these geometries from? How do these geometries come into existence? We mentioned that as we create the molecules, that there are electrons, whether they're unbonded or bonded pairs, that electrons all have negative charges, therefore they all repel one another. Okay? And that the molecule seeks a state of equilibrium to the place where everything is repelling each other as far apart as it can possibly be. And it can go no farther without becoming closer because it's 3 dimensions. It can't go farther away from something without becoming closer to something else. So it finds a place where the forces are evenly distributed, with the one caveat that an unbonded pair exerts more force than a bonded pair on that geometry. And because of those repulsions of the electron pairs, whether they're an unbonded pair or a bonded pair, as they repel one another, it forms the geometry of the molecule. And we talked about 5 specific geometries. Now, if you want to look at table 5.2, they lay out the 5 geometries there as well. However, they teach it in the reverse order. And I think the way that they teach in reverse order isn't quite as effective as the order I taught it in. Okay? I mean, I don't teach a weird way just so you get messed up, but when the easy way is in the book, right? Hopefully I teach you a way that'll make sense to you. This is correct. It's just for me, I believe, and for my experience in teaching this class, that it works better rather than starting at linear and progress up to those based upon a tetrahedral, is to start with a tetrahedral and then work down from there. Okay? So, 5 basic geometries. What's one of them? And maybe look at your notes, but spend more time up here. Just try to remember. Yes, sir? Tetrahedral? Okay. What is the characteristics of a tetrahedral? When you first look at the molecule, what kind of things are you going to notice about its construct that's going to lead you to think it's a tetrahedral? Okay, so we're going to talk about the central atom or the pivot atom. And that central atom, if we did a 2-dimensional Lewis structure, it's the one that we put in the middle. It goes into the middle because it has the highest number of unpaired electrons. Okay? And we look at that central or that pivot atom, that's the pivot central atom of this molecule. For it to form a tetrahedral, it's going to have 4 points of connection. When we drew the Lewis structure, it's going to have 4 different connecting points. Okay? What's something else about the tetrahedral? It has 4 points, and what is at every one of those points? A bond. Okay? So it has no unbonded pairs. It has 4 points, and at every one of those 4 points, there's a pair. Matter of fact, at every one of those 4 points, there's a single covalent bond, right? Because 4 times 2 is 8. It's going to give that central atom its octet. So it has 4 points of connection. All 4 of those points of connection are filled with a covalent bond. And what is the bond angle, ma'am? 109 degrees. So that 109 degree bond angle, that is the angle between any 2 bonds. Using that pivot atom, that central atom, as the, where the angle is at, the vortex there. Okay, the vertex. So these 2, this bond and this bond, what's their angle? That bond through the central atom out this bond, it's going to be 109 degrees. And every one of them is 109 degrees because those bonds are seeking to repel one another as far as possible. And we said that in 2 dimensions, the farthest you can repel is 90 degrees. But real life isn't 2-dimensional, it's 3-dimensional. Okay? So we have height, depth, and width. And they repel one another not to 90, but they repel one another to 109 degrees. The tetrahedron, this is the first shape over here. So it's a tetrahedral. And again, 4 points of connection. Here's the central atom. 1, 2, 3, 4 points of connection. Every one of those points of connection has a connection with a bond. Every one of these bonds are equidistant from one another, sets up the same angle in any direction from any bond to another bond, and that is 109 degrees. Okay. The second shape we went over is based upon the tetrahedral. And what is that one, ma'am? Pyramidal, or trigonal pyramidal is the full name, but we can just call it pyramidal. I'm stuck with knowing its formal name, so if I say trigonal pyramidal, just hear the second word I say. Just like when I say planar trigonal, it's just trigonal, okay? So this is a trigonal pyramidal. What's the difference between, now this one is based on a tetrahedron, but it's not a tetrahedral, okay? It has, what's the difference between the 2? Go ahead. Yeah.
It has 3 bonded and then 1 unbonded.
Okay, so it still has 4 points around it, but one of those points is occupied by an unbonded pair, and the other 3 points have bonds on them. And what is the bond angle? Ma'am?
107 degrees.
Good, 107 degrees. It's a pyramidal, 3 bonds, 4 points. We've got 1 unbonded pair. That's 107 degrees. Looks like this. This is my 3-dimensional model. Okay? 4 points. 3 of them have bonds. 1 of them has an unbonded pair. Before, if this had been a tetrahedral with a bond, the angle would have been 109 degrees in all directions. However, now we don't have a bond, we have an unbonded pair. And the only places I have angles are between these 3 in all different directions. Okay? Now, because we replace the bond with an unbonded pair, this unbonded pair pushes the others away with more strength than a bond would. And so the effect is, it's pushing away stronger than if it had been a bond. So what used to be 109 now gets squeezed down. So these bonds get squeezed closer together by 2 degrees. And so the angle changes from 109 to 107 degrees. Okay? So again, it's based upon a tetrahedron, or based upon a tetrahedral because it has 4 points around the pivot atom or the center atom. It's a pyramidal because it looks like a tripod. Remember we said look at the camera? There's the 3 legs and the camera on top. That's the form it takes as opposed to a pure tetrahedral. Okay, one more shape based upon a tetrahedron, but it's not a tetrahedral. What was that one? Molly. It's a bent. Okay? So we're walking, we had a full tetrahedral, 4 points with 4 bonds, and then we have pyramidal with 4 points and 3 bonds. Can you guess what a bent is? Yeah.
2 bonds and 2.
Okay, so it still has 4 points, but it has 2 bonds and 2 pairs. And the effect is the same as replacing 1 bond with a pair. Now that we have 2 bonds, or excuse me, 2 bonds and 2 pairs, that other pair squeezes these bonds even closer together, repels them even more apart. So here I have 4 points of connection, 2 bonds, and 2 unbonded pairs. Forms a bent Now there is another bent which you don't have to memorize, just so you know that there is one. We'll get to that in a moment. So these are the three shapes, all based upon a tetrahedron. The tetrahedral, 4 points, 4 bonds. The pyramidal, 4 points, 3 bonds. And the bent, 4 points, 2 bonds. Each one has 2 degrees less of separation, the bond angle, 109, 107, 105. Okay? So you can see how the key to this is, first of all, being able to draw the two-dimensional Lewis, and then just bringing it forward into 3 dimensions. Right? Okay, so any questions on that review right there? It's a pretty quick review, but I mean, that's the guts of what we did on these shapes. We've got 2 more we need to discuss. One more I'll show you that we didn't discuss, but just so you know it's out there. Because I made the model for it, I'm not going to waste all that time and make a model, not get to show it off, right? So another thing you might want to notice here is it's going to be based primarily upon your two-dimensional Lewis structure, but think about the two-dimensional Lewis structures. What do we typically see that has 4 points of connection that will form a tetrahedral? What kind of an element? Column 4A, right? Column 4A, have 4, need 4. Would love to have 4 shared electrons to complete their octet. So these are going to tend to be column 4A elements. So what do you think pyramidals are going to tend to be? They only need 3 because they've got 5, right? So they tend to be, if you have a column 5A element, it's probably going to be a pyramidal. And guess what bents look like? If you have a column 6A element, it has 6, it only needs 2, and it can get them by sharing 2, by forming 2 bonds. So when you first look at the elements that are involved, if you have a column 4A, 5A, or 6A elements, you've got a head start probably. Still do the two-dimensional Lewis to check it out, because there are exceptions, and it's not simply based upon that column, but a column 4, column 5, and column 6A elements tend to be the pivot atom in those types of molecules. Okay. The next type we talked about was the trigonal planar. Obvious here, it's a central atom that has 3 points of connection. Those 3 points of connections are all bonds. So what does the geometry work out to be? What's the bond angle? 120, because 120 plus 120 plus 120 is 360. Now it naturally lays itself out in a plane, okay, which is why it's trigonal planar. It's in a plane already. Remember on those other geometries, the way we do it is we put if there are, let me just show you again, if there's a tetrahedral, kind of stepping back just a moment, if we have a tetrahedral, what we're going to do is we're going to put 2 of them, the pivot atom and 2 of the other atoms in the plane of the board. We're going to draw it like this. And now we have 1 atom that's coming towards you and 1 atom that's going behind you. Remember how we drew that? I don't have a slide to re-show that. But this would be a thin triangle coming forward to indicate it's coming out of the plane towards you. This back one is a hashed triangle. It's going away from you, back into the plane of the board. We always are going to try to orient the unbonded pairs in the plane of the board. So in this case, I can show this to you and you go, oh, it's a bent molecule, 2 bonds, 2 unbonded pairs. How do I draw it? We're going to go ahead and place those in the plane of the board, 1 at 12 o'clock and 1 at about 4 o'clock. And then how are you going to draw it? Well, 1 is coming towards you and 1 is going away from you. So it's really going to come down to the same basic shape. It's either going to have 4 bonds, an unbonded pair and 3 bonds, or 2 unbonded pairs and 2 bonds. So your triangle coming out and your triangle going back are going to be the same in every case, just whether or not you're going to have a bond or an unbonded pair. All right. So we did the trigonal planar. Remember, Vesper tells us that all of these bonds are trying to repel one another and be as far apart from one another as possible. You can see that they're equidistant. That symmetry comes from that even forces pushing everybody away. Because if this one wants to get farther away from this one, it has to move closer to this one, and they'll repel each other this way. Nothing can move closer, or nothing can move farther away from one without moving closer to another. And it's that constant repulsion that takes place that keeps it in this perfect symmetry. Also in the plane, nothing can come and bend this way or this way, for example. If it bent this way, it would be closer to these. And so it gets pushed back. And if it was pushed this way, it would be closer to those two again. It would be pushed back. So every atom is in a place where it can't get any farther away than it is currently. Okay? If there was a way that it could reconfigure itself to be farther away, it would. It can't. It can't get farther from one without getting closer to another. And that's why the geometry falls out in this way and is very stable. All right? So this is the trigonal. Trigonal has 3 points, 3 bonds, 120 degrees. Now the one we didn't do, and I'll just show it to you since, of course, like I said, I made the model, so we might as well show it, is, and you don't need to put this in your notes because I don't believe it ever comes up, but it's based on a trigonal, but it only has 2 bonds. Okay? It's referred to as a bent molecule as well. It's a different kind of bent. That's why I think we only keep one of them, because the other bent is like water. We use it all the time. This one, not so much. But you can see the difference here. If a trigonal is 120, we replace one bond with a pair, what's going to happen to this bond angle at the bottom? Just apply the same principles. If I replace this bond with a pair, what have I done? What's going to happen? Okay. Normally the bond is repelling at a certain amount. If I go ahead and do a quick exchange, take the bond off, put a pair on, how's the pair react? How do they react to a pair relative to how would they act to a bond? Sir?
The pair has a stronger repulsion, so
good. So when this has a stronger repulsion, it will
force them further apart.
it'll force them farther apart from themselves. So it'll be farther away from the pair, which means they'll be closer together to one another. And so this is a bent molecule, like you might want to call it a trigonal bent or something like that, but the angle here is 116 degrees. So it goes from 120, replace it with a pair, they get squeezed together to 116. That just maybe bonus points, you know, but you don't have to know it for core. And the last geometry we did. Do you recall? The linear, right. It's a line. What's an angle for a line? You know, if you had a vortex and it lays out flat, it's 180 degrees, right? So we get this linear from 2 different ways. 2 points of connection and 2 bonds. So that means, for example, if we have we could have 2 double bonds, because single bonds, double bonds, triple bonds, they all count just as a bond in Vesper. But so here we've got 2 points of connection, both with a bond. So we've got 3 atoms connected by 2 bonds. They're going to lay out in a straight line. They can't get any closer to one another. They don't want to. And this is as far apart as they can be, is straight line. The other way we can have a linear molecule is to not have a pivot atom, which means we only have 2 atoms connected to one another. And we used a homonuclear diatomics as an example of this. So every geometry assumes that there's some pivot point, being the pivot atom, the central atom in the molecule. When you have a homonuclear diatomic or any other 2-atom molecule, there is no pivot point. All they have between them is a bond. And so that is considered to be a linear molecule as well. 2 or 3. Ends drawn as a straight line. Okay? So that's a quick review of that. What we're going to do is example 5.2. We're going to walk through that together, and then we're going to do on your own. And that's the intent for today. If we have enough time, I would love to get into polarity, polar bond, and non-polar bonding, but I'm not pushing for us to get there. So we're going to be doing some whiteboard work. Let me go ahead and put the screen up. And answer the question. Example 5a says, what are the shape and bond angle of a PHCl2 molecule? I'm not going to go ahead and try to name these molecules, okay? We're just going to go ahead and, unless it's obvious or I accidentally name them, but just the PHCl2 molecule. What is the shape and the bond angle? Now it's in your book, so if you follow along in the book, that's fine. If you want to follow along up here and review the book at your own, that's fine as well, whichever you think will help you learn it better. But let's start by what is the molecular geometry of a PHCl2 molecule? How are we going to start to answer this question? How should we start?
Figure out what columns they're in.
Okay, because what are we doing first? We're looking at our two-dimensional Lewis structure. We're going to draw a two-dimensional Lewis so we can do the three-dimensional Vesper. Okay, that's the way we're going to understand it. We're going to go from a 2 to a 3, convert from one to the other. So let's go ahead and do the two-dimensional Lewis for a PHCl2 molecule. First question you have to ask yourself is, what's going to be the pivot atom? Is there a pivot atom? Yes, there is, because there's more than 2 atoms involved. So something's going to be the center, right? Something's going to be the one that has the most unbonded pairs, or most unbonded electrons. So, of those, which one is going to be our center, ma'am?
Phosphorus.
Okay, good. So at this point, you don't necessarily need to draw a Lewis for phosphorus, a Lewis for hydrogen, and a Lewis for chlorine. Hopefully you're looking at it and saying, okay, it's a 5, 1, 7. It has 1 unbonded, it has 1 unbonded, it has 3 unbonded. That's my center, okay? Now, before we even do this, what hint did I give you earlier? If phosphorus is our central pivot atom, and we look to figure out the electron dots for that, we look over and find out that phosphorus is what column? Column 5A, right? So it has 5 valence electrons. Okay? What shape is probably going to come about because of a column 5A? Do you remember? Pyramidals. Column 5A hubs, central atoms, tend to form pyramidals. Let's see if that's what happens. So I have phosphorus in the center. I put my unbonded pair on the top, and I've got 3 points now. Looking at that, everybody agree that's my central atom, that's my Lewis structure. How many points of connection do I have on phosphorus? How many points of connection?
3.
We got 4 points of connection. One of them is filled with a unbonded pair, okay? So we said before it's probably going to be a pyramidal, but now I can say it's probably going to be, this is a little less information, it's probably going to be based on a tetrahedral, right? It's probably going to be based on a tetrahedral because I've got 4 points around the central atom. And I'm leaning towards being pyramidal because one of them is already filled. So the most I can have is 3 bonds, which will form a pyramidal, which is a modification of a tetrahedral. So I kind of work it, you know, if I don't look at that and say, hey, it's a column 5A element, it's probably pyramidal. If I didn't know that, I could start with, look at that. It's probably a pyramidal because I've got 3 potential bonds. But let's see if it actually lays out as 3 single bonds, because what's going to mess that up is if I've got any doubles or triples, right? So I still need to keep doing the process. So the chlorines are 7s, right? Hopefully we're good with that now. So chlorines are 7s, and I'm going to bond them in a hydrogen. Okay, now I dropped doing the 6 dots around both the chlorines, because now we're toddlers now. We can say, I recognize that there's 6 more electrons around there, Mr. Baker, but I don't need to see them because I've got 6, 7, and sharing that one with phosphorus, and there's my 8. So hopefully you can see that chlorine sees 8, chlorine sees 8, hydrogen sees 2, phosphorus sees 8. So that's my two-dimensional Lewis structure. I have a central pivot atom, 4 points of connection, 3 bonds. It fits the bill for my pyramidal, doesn't it? When I draw it, then, I can draw it central phosphorus, actually I usually do it as a dotted, but this is hydrogen. Okay. So I have phosphorus, an unbonded pair, and my chlorine. Then I have another chlorine that's coming out of the board towards me, and then I have another hydrogen which is angled back into the board. So what's the shape? To say it, I mean, we've said it several times, but what's the shape? Pyramidal. Technically, it's a trigonal pyramidal. What is the bond angle? 107. The tetrahedron is 109, pyramidal is 107, bend's 105. Goes down by 2s. Okay? Where is that angle at? Where is it 107? It's 107 here. It's 107 here. It's 107 on the back side over to there. But it's not here and here. The bond angle is between bonds, not between a bond and an unbonded pair. That's why it goes from being 109 to 107, because we're making the angle from the unbonded pair to the bond even greater. It's going up. And when it goes up, the others have to come down. Okay, so yes, it's a trigonal pyramidal bond angle of 107 degrees. What's the shape and bond angle of an SiO2 molecule? Okay, just from a symmetry perspective, what's going to be the central atom? Silicon. Good. I've got 1 silicon and 2 oxygens. I'm going to assume that the oxygens are going to be symmetrically placed around the silicon. And as a matter of fact, when I do silicon, how many valence electrons does silicon have? Remember, that dot is not an electron, so I'll place it with an X. 4 of them. Good. So I have 4 around silicon. Now, I might stop and say, looks to me like I've got a tetrahedral going on here. But that's where you've got to stop and go, okay, I'm going to hold on to that lightly. I'm going to hold on to the idea that I've got 4 points of connection around the silicon lightly, because doubles and triple bonds mess that up. So next, drawing the 2-dimensional Lewis, I have to place the oxygens. Oxygens are column 6A elements, so they're going to have 6 dots. Now I know they're forming a molecule, so I have to start with at least a single bond between them. There's my single. There's my single. 2, 4, 6, 7. 2, 4, 6, 7. 2, 4, 5, 6. Nobody's happy. How do I complete the octets? Ma'am? A little bit louder. All right, I'm going to bring the unbonded electrons towards each other and bond them. Now, how's it look? Are we good? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Octets are full. That's my 2-dimensional Lewis. What's my 3-dimensional Lewis look like? There. Yeah. It's a linear. Because the angle between the bonds right here is 180 degrees. And the only difference technically is that I set around each oxygen, I set it like trigonal, right? I've got 3 different points. So rather than having it be here and here with nothing there, I kind of shifted them around. Why? Because I'm recognizing that these things are kind of repelling each other into 3 equidistant spots. So I just kind of rotate the dots around a little bit, but I don't do anything radically different to it. Right, so the silicon dioxide is a linear molecule with a bond angle of 180 degrees. So I don't have any coming in, going out. None of that is taking place. Okay. Any questions on that one? Silicon dioxide. What's the shape and bond angle of an OCl2, an oxygen dichloride molecule? Okay, so what's going to be my central atom? OCl2. Oxygen's a 6A, chlorine's a 7A. Chlorine has 1 unbonded pair, oxygen has 2 unbonded pairs. Oxygen's my center. So I have an oxygen here. Chlorines, I have two of them. They have one unbonded. Form them with singles. Check the octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. The octets are all satisfied. I'm done with the two-dimensional. Okay? Can you see what this is in 3 dimensions? And what is it? Bent with a bond angle of somebody else. 105 degrees. Good. Okay? This is the same molecular geometry as H2O, water, right? Hydrogen has single bonds to an oxygen, same layout. It's going to look like oxygen with an unbonded pair, an unbonded pair, chlorine coming out of the board, and chlorine going back into the board. The bond angle of 105 degrees is the angle between these two bonds right here. It's not the angle between anything else. It's just those two bonds of 105 degrees. Cool? Give me a bobble, yes or no. Got this? Okay, good. Let's go ahead and move on. Just because I want to make sure we hit all the different cases. At least the ones that they've already offered us. 5D, what's the shape and bond angle of a BF3 molecule? Let's think about this one for a minute. Now, there's something you may not know, what they give you in the book, is that boron is an exception. It's a weird atom in the sense that it only wants to have 6 electrons in its valence shell. It's an exception to the octet rule. It wants 6. So knowing that it wants 6, boom. What is the two-dimensional Lewis structure for a BF3 molecule? Okay. How many electrons does boron have in its valence right now? 3, okay. So two-dimensionally, I put them at 3, 6, and 9, right? What about fluorine? Fluorine's one of our 7A elements, right? So it has, like chlorine, 1 unpaired and then 6 paired. And I'm not going to draw the 6 around it, but there are 6 around it. I'll put another one down here, unpaired and then 6. Fluorine, 1 unpaired and then 6 paired. Single bond them, right? Ask the question, are the octets full? Fluorine, 6 plus 2 is 8. 6 plus 2 is 8. 6 plus 2 is 8. Boron, 2, 4, 6. Are the octets satisfied? Yes, they are, because boron's the exception. It only wants 6. So they're satisfied. This is the two-dimensional Lewis structure. How do I write the three-dimensional Lewis structure? First of all, what shape is it going to have? Ma'am? Right, it's a trigonal planar, right? It's going to be a trigonal. So I've got BF3. That's in 2 dimensions. In 3 dimensions, it becomes like that. It has this shape. Single bonds, but 3 bonds with only 3 attachment points. Each one equally 120 degrees apart. Nothing coming in or out of the plane of the board. It's all in the plane, which is why we can show it this way for 3 dimensions. Okay? So it's trigonal planar. We've got several more. Are you having fun yet? At least somebody is. I am. This is cool stuff. This is some of the funnest stuff for the year. So let's just keep on going. I'll be the weird chemistry teacher. Determine the shape and bond angle of an oxygen molecule. Do we need to do any work here? Right? An oxygen molecule. How many atoms are in an oxygen molecule? 2. It's a homonuclear diatomic. It's 2. What is the bond angle and the shape of every molecule that has only 2 atoms in it? It's a linear. It's 180-degree linear. Because the connection between 2 atoms is always, there's no pivot, right? It's got to be a straight line. And so the oxygen is a linear 180-degree bond angle because there is technically no angle. On your own 5-5, determine the shape and bond angle of a CHCl3 molecule. Just right now, imagine in your mind, okay, CHCl3. What's it going to look like in 2 dimensions? Can you see the 3-dimensional shape already? And let's start to walk through it. What is going to be my pivot atom? Carbon. How many points or how many unbonded electrons does carbon have? 4. Carbon is going to tend to be, silicon is going to tend to be forming these tetrahedrals, right? It has 4 points of connection. It's probably going to be a tetrahedral. I've got chlorine and hydrogen. How many do they want each? I've got 4 of them, right? I've got a hydrogen and 3 chlorines, and each one of them want how many electrons? Do you see that each one of them wants 1 more? Chlorine is column 7. It wants 1 more. Hydrogen, column 1, but it wants 1 more because its octet is satisfied with 2. They all want 1. I've got 4 kids all wanting 1 and 1 parent that has 4 to give. Guess what? They're going to latch on to all those 4 points, and it's going to form a tetrahedral. It's going to be CHCl3. Bond angle? What's the bond angle here? It's a pure tetrahedral. What's the bond angle? 109. Tetrahedral, 109. Pyramidal, 107. Bent, 105. Trigonal planar, 120. Linear, 180. What's the shape and bond angle of arsenic trichloride? Arsenic trichloride. Take a moment. Try to figure it out. Get a little bit ahead of me. Arsenic is AS on the periodic table. It's a column 5A element. If I told you you had a column 5A element, what would your first guess be that you're probably dealing with? Pyramidal, trigonal pyramidal, okay? I have 5, it's a column 5A element, I have 5 valence, I have 1 pair, which means I need 3 bonds. I'm probably looking at a pyramidal, okay? The fact that I've got trichloride, I've got 3 things, and I've got 3 attachment points open, don't I? 1 attachment point has got a pair on it. I've got 3 openings for bonding, and I've got 3 chlorides that want to bond. Have 3 connection points available, have 3 participants who want to bond with me. Guess what? I bond. And I end up with, in 2 dimensions, arsenic trichloride. Again, seeing that every one of these chlorines has 2, 4, 6 unbonded pairs around them. Okay? Hopefully you're seeing that now without me drawing it. So there's 2, 4, 6, and the bond makes 8. 2, 4, 6, and the bond makes 8. 2, 4, 6, and the bond makes 8. 2, 4, 6, 7, 8. Everybody's octet is full. This is a correct two-dimensional Lewis. Oh, it would be a tetrahedral if I had 4 bonds. I've got 4 connecting points, 1, 2, 3, 4. One of those connecting points has an unbonded pair. If I had 4 bonds, it would be a tetrahedral, but I don't. I have 3 bonds and an unbonded pair, which means my shape is now a trigonal pyramidal, or just pyramidal. And I draw it as arsenic with the 2 dots, slightly greater than 90-degree chlorine, 1 chlorine coming out of the board at me, and 1 chlorine going back. And I've set up my tripod. Not good. Set up a tripod with my camera on the top. Okay? That's my arsenic trichloride. Any questions on arsenic trichloride? Now the test. The shape and the bond angle of sulfur dibromide. Have an answer. Go ahead and work it. Sulfur dibromide. So please started by drawing the two-dimensional Lewis, right? Sulfur dibromide. So let me talk you through the two-dimensional Lewis structure. What's going to be my pivot at? Sulfur. Okay. How many valence electrons does sulfur have? 6. 6A element. Okay. So 1, 2, 3, 4, 5, 6. Dibromide. Bromide is a column 7A element, so it has 1 unpaired electron it's looking to pair with 1 unpaired electron to form a bond, right? Okay. Again, do you see that there's 6 plus that 1 makes 7? 6 plus 1 makes 7, and I form the bond here and here. So this bromine's complete, this bromine's complete. 2, 4, 6, 8 sulfur is complete. That's my two-dimensional Lewis. What does that convert into in three-dimensional Vesper? Bent. Good. 4 points of connection, 1, 2, 3, 4. 2 of them have bonds and 2 of them have unbonded pairs. If it was 4, it'd be a tetrahedral, but it's not. If it was 3 bonds, it would be a pyramidal, but it's not. So it's 2 bonds, which makes it a bent. If it was a tetrahedral, it would be 109 degrees, but it's not. If it was a pyramidal, it would be 107, but it's not. So therefore, it's 105. 105 degree bent. And we're going to draw that. A pair, a bromine coming out, and a bromine going back. Right. You only have one more on your own. That's the shape of an SiCl2O molecule. Real quickly, what's going to be your hub?
Silicon.
Silicon's going to be my hub. It has 4 points of connection. But how many things bond to it? 3. Oh, wait a minute. If only 3 things bond to it, how many connecting points do you think we're going to have? We ideally have 4, but we've only got 3 things bonding to it. So we're probably only going to see 3, right? So if I've got silicon here with 1, 2, 3, 4, 2 chlorines that want to bond like this, right? What am I left with? Oxygen? How many does oxygen have? It's got 6 electrons. 2 of those are unbonded. I put 1 there. I need this one to match with this one, right? Okay. So what's my shape? Okay. You have 1, 2, 3 connecting points with 3 bonds, so it's a trigonal planar.
Whoa.
120 degrees each. So it's going to look like nothing coming in and nothing going out. Actually, this is wrong. This is a double bond right here. Remember, double bonds, triple bonds, single bonds, for Vesper, they all have the same value in terms of repulsion.